All right. First unit, introduction to brute force method. Okay. Description of brute force method. Okay. Yeah. It's a straightforward approach. Okay. So we do not use any fancy technique. We just do it in a straightforward way. Okay, no trick, the simplest way, okay, direct way. Okay. You can always apply it to a problem. Given any problem, the first thing you can try the brute force method. The first, everyone can try it. Okay, brute force method. Okay. In general, it is not the best algorithm. Okay? In general. But in some special case, it could be the best, right? Yeah. Sometimes, straightforward, it's already the best solution. Yeah. Okay? It's possible. Yeah. But that's usually for easier problems. Okay? It is usually used as the starting point for more advanced algorithms. Yeah. Now, our goal, we want to find the most efficient algorithm. But because at the beginning, we do not quite understand the problem. So we try the brute force method to help us understand the problem. That's why that step also useful for us. Yeah. The efficiency difference between the brute force method and the more advanced could be huge. Yeah. Later, the difference is extremely big. Yeah. Here, let's use the polynomial evaluation problem. Our problem number 1 for this class, we compare the difference. Remember, 500 million to 1 ratio, right? 5.8 days versus 1 second, right? Yeah. We compare that difference. Huge difference. That 5.8 days, that's the brute force method. That is the brute force method. Okay. That 1 second, that is, we use the Horner's rule. We use Horner's rule, that method. So you can see the difference is huge. Okay? Yeah. Bubble sort. Now, let's use this brute force method. Yeah. Even the brute force method, we have many different ways to use brute force, right? Here. I want to use this bubble sort to show you another way to use the brute force method. Our selection sort, we can treat pretty much brute force. Also brute force, pretty much. Okay? Yeah. Yeah. So this bubble sort, another brute force method. Okay. Why we need to solve it another time? Yeah. So this same problem number 4, we solve another time. And for this class, we will solve 5, 6, 7, many times this problem. Because we have so many different sorting algorithms. We need to learn those sorting algorithms. So that's why we solve it many, many times. Okay? Yeah. Here we change a view. For this question, we change our view. Every time when we change our view, we may get a new solution. Here, we want to get a new solution. Okay? Yeah. So, our view so why we do it in this way? Yeah. So here, I give you that view. A problem is a carrier of a set of thinking methods. We look at so this problem has so many solutions. It carries all those different thinking methods to solve that problem. So it is a carrier. It has a lot of values. Okay? This sorting problem, it carries so many different solutions, thinking methods. So we need to learn those thinking methods. Yeah. So that's why we treat that as valuable, treasure. Yeah. Right? Yeah. The thinking methods are important to help us solve other problems. Yeah. After we are equipped with those thinking methods, we can solve many other problems. Yeah. So that's the reason we solve this problem repeatedly, okay, using different methods. Yeah. All right. Explore. Now we need to solve it. We explore a property for the bubble sort, the key property for the bubble sort. Okay? Yeah. A view based on a special property. This time we try to get a different property. So we will get many, many properties. Okay. So this time when we view in different angle, so we get a different property. And we will use that to get a different solution. Okay. All right. What is that property? Let's look at this diagram. Okay. Yeah. Try to examine this array, given an array like this. Okay. All right. Let's do some analysis. Observation. What kind of observation do we have on it? This time we take a local view. Local view, global view. Okay? Local view. Sometimes we take local view. Sometimes we take global view. Okay? This time we take a local view. Okay? So what kind of local view do we take? Okay? If the array is not sorted, let's make this assumption. If this array is not sorted, what property do we have? So we assume it's not sorted. So what conclusion can you get if it's not sorted?
There is some A sub I that is greater than A sub I plus 1.
Good. Good. That's the one. Okay? That's the one. Okay? All right. So let me describe in this way. If the array is not sorted, there must be two adjacent elements. Okay? Here, let's use these two adjacent elements. They are out of order. Okay? So suppose we want to get increasing order, but out of order, so the first one is greater than the second one. Out of order. Two adjacent ones. Two adjacent, why we look at two adjacent ones? Why you do that? That's why I say local view, right? We only look at locally, yeah, in a small local area, right? Local view, yeah. So, because if we can find this property, then our algorithm design will fix this property. Can we fix it? Yeah. We change it, we fix it. That's the idea. Yeah. The property, we find it, we identify this property. So after we fix it, we get this array sorted. That's the idea, right? Yeah. So here, you can see the idea is so simple. Yeah. All right. Out of order. That's the key property. Yeah. Yeah. Next, we want to describe this out of order property a little bit. Okay. Yeah. All right. How to fix it? Do you know how to fix it? If you know these two elements are out of order, how do you fix it? Swap. One operation, one swap. You fix it. Okay? Can you extend the idea? Can we try to first detect out of order adjacent pairs everywhere? After we detect it, swap operation, we fix it. Okay? That's the whole algorithm. Okay? That's the whole algorithm. Yeah. All right, swap operation. Okay. Next, let's look at a swap operation and inversion concept. Inversion concept. So that out of order, we use a formal terminology we call it inversion. We define inversion for that out of order phenomenon. Okay? Inversion. What is the inversion definition? Yeah. Reference I'll give you here. Okay. Yeah. A pair of elements, A sub I, A sub j, but not necessarily adjacent. Okay. Anywhere, right? Anywhere. The general definition of the inversion, not necessarily adjacent. Okay. Anywhere is called an inversion if, when I less than j, ai greater than aj. Yeah. That order is different. Yeah. Because in a sorted array, if I less than j, ai should be less than or equal to aj in a sorted array. This means if you have one inversion in your array cannot be sorted. Okay? Yeah. So if your array is sorted, there is no inversion. Okay? Yeah. So this is the definition. Okay? Yeah. Yeah. All right. So observation, if the array is not sorted, there must be an inversion. Adjacent or not, there must be an inversion. Okay? All right. But can we say a little more? We rewrite our previous property. Yeah. So this observation, we do not say adjacent or not, those two elements. Can we make stronger claim? If the array is not sorted, there must be an adjacent inversion. How about that? Adjacent. Yeah. So if far away, but you can try to get a adjacent inversion, right? Yeah. You can get an adjacent inversion. Yeah. 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 So by your intuition. Yeah. So here we do not prove it. By your intuition. Okay. Yeah. All right. Sorting problem by local swap. The solution, after you have this view, the solution is immediate. Okay. Idea. Remove all the local inversions by local swaps. That's our main idea of the solution. Okay. Local inversions, local swaps. Okay. All right. Procedure. Step 1. Start from the first element for each scan. Okay? Every time you scan the array, you start from the first element. Okay? When you do your scan, do swaps one by one from left to right. Oh, yeah, if necessary. Yeah, I need to add if necessary. Okay? So you check. Okay? Two adjacent elements. If you find an inversion, you do swap. Okay? Otherwise, you don't do it. Okay? All right. Step 3, stop at the first in-place element. Because, think about it, after you scan once, which element is at the end?
It's the largest.
Largest. Right? The largest element will move to the end. Can we say that element is in place? Yeah, it is in place. All right. Then we do next another scan. In our second scan, do we need to look at that? No, we don't look at. So we stop immediately before the element that is already in place. Okay? So our second scan, we will put the second largest in place. Another scan, third largest in place, and so on. So every time we stop at the first in place element, then, because it's already in place, so we don't need to do anything. Okay, so we just do another scan. All right, yeah. So we summarize the property. There is one element in place for every scan. Okay, yeah. The in-place element of each scan appears at the end of the current array. Yeah, the largest of the current array. So it is at the end. Okay? The current array is a subarray that excludes all the in-place elements. Yeah. So with this kind of property, now we understand the problem completely. Okay? Yeah. So this kind of analysis, that's the procedure we try to understand this problem well. Okay? Then we can write the code. Yeah. So our next step, we write the code, pseudocode. Okay. All right. Yeah. Visual imagination. So why we call this sort bubble sort? Right? So visually, use your visual imagination. The swab looks like bubble moving to the right. Yeah. So that's why, using some visual imagination. Yeah. Just like a bubble, okay? Yeah. Moving to the right. Yeah. All right. Implementation. Yeah. Now we are ready to write a pseudocode implementation. Okay. Bubble sort. We pass array to this algorithm, to this function. Okay, yeah. From I, so your I index, from 0 to n minus 2. N minus 2. Yeah. Because that's the one you want to compare to adjacent elements. So the last pair starting from n minus 2 index. So that's why the last one, I, n minus 2. Okay? I use to indicate the current scan. Yeah, current scan, every time when you do scan, your I, moving from 1, yeah. So I moving from 1 to n minus 2. So, oh, yeah. So, because you need to, all right, so here, this I corresponds to your scan number. The first scan, you choose I equals 0. Second scan, you choose I equals 1, and so on. So you do n minus 1 scans. N minus 1 scans. Okay? Yeah. All right. Inner for loop. Inner for loop. J also start from 0, but you stop n minus 2 minus I. Okay? The first time, in your first scan, your J stop n minus 2. Okay? Yeah, the last pair. Second time, when I choose 1, your J stop at n minus 3. Okay? Every time your J stop at 1 position earlier. Okay? Yeah. So that's why you control that J. Yeah. Inside, all right. So yeah. So swap. Inside, you check if two adjacent elements form an inversion or not. Yeah? This means inversion, right? This means inversion, adjacent inversion. When you detect adjacent inversion, you apply swap operation to fix it. Okay? Yeah? So that's the bubble sort. Question?
Why does it go to n minus 2 instead of n minus 1?
All right. N minus 2. This element, its index n minus 2. Okay? So it stopped at that because, think about, all right, so let me answer your question this way. Actually, this is a pretty good question. Let me answer it this way. Okay. Yeah. I from 0 to n minus 2, we have n minus 1 numbers, right? That means we have n minus 1 scans, right? Every scan, you put one element in place. After n minus 1 scans, you put n minus 1 elements in place. Then you only have one element left. It must be in place, right? So you do n minus 1 scans, you put n minus 1 elements in place. It's already good enough to sort the whole array. So you do not need to do one. If you do one more, you do one redundant scan. Okay? Suppose you n minus 1, you do one more scan. It's redundant. Because already in place, why you do another time? Right? It is already in place. All elements all in place. It's sorted. Don't do anything. So that's why we just stop. Okay? Yeah. Because we know the whole array is sorted. So we stop. Yeah. Very good. So let me just stop here. Question? Anyone? Yeah. All right.